All right, section 1.4 is trig. This is all should be review. So I'm not going to spend a ton of time on it. I'm just going to go over a little bit. Be good with you. All right, so sines. Okay, remember sine is this function here. It is, it starts at the center or the equilibrium, if you will. Goes up and then back down. Okay, we're not going to talk a ton about today, but I do want to mention this. Remember the amplitude. We're not graphing them, but I do want you to know this. The amplitude is 1. The highest it ever gets is 1. The lowest it ever gets is -1. Boom, boom, up and down it goes. Recall the period, the time it takes to replenish it, or to do itself, is 2 pi. Or if you prefer, 360 degrees. Okay? Remember that cosine is similar to it, except, of course, it starts at the upper extreme. Okay, so cosine. Okay, starts up, also has an amplitude of 1, also has a period of 2 pi. Okay. Piece of cake. I think we're pretty good with that. What would happen if you had negative sine? Negative sine, what does that do? Well, it takes everything's positive, makes it negative, so it's going to do this instead, right? And negative cosine, same thing, like so, right? That's all should be reviewed. It should not be a thing. I don't want to spend a ton of time on that. You do remember reading or seeing this chart, and you may have forgotten it, but I'm going to run over it again. So the angle in radians, angle in degrees. This needs to be tight in your head, so don't forget it. Cosine, sine. Okay, and so 0, 30, 45, 60, 90. Those are the biggies, if you recall. 180, I should probably throw him on there just for fun. Okay, oops, I got those backwards. So this is the angle in degrees first. Angle in radians we'll do second, I guess, because 0 radians is 0 degrees. That's kind of cool. .30 degrees. Remember, 2 pi is 360 degrees. That's all the way around the circle, right? That is the distance around the circle is 2 pi radians. So that's the same as 360 degrees. Pi is 180. And then Mr. Grimm just remembers this way. Well, wait. To get to 30, you take 180 and divide by 6. So pi over 6. To get to 45, you divide 180 by 4. So pi over 4. To get to 30 degrees, or to 60 degrees, that's pi divided by 3 then. To get to 180, it's pi over 2. And of course, this is pi, right? Piece of cake. So cosine here is 1. If you remember on your unit circle, cosine is to the right. Everyone mentioned that, right and left rather. That's 1 unit. It didn't go up at all. Of course, this is backwards because you went straight up, obviously. This one is -1, 0. Okay? Now, what about 30? So 30, Mr. Grimm, I forgot it. Good, memorize it. Square root of 3 over 2. 1/2. But if this is 30, this is 60, correct. So when you flip-flop it, those two flip-flop, correct. So 1/2 square root of 3 over 2. Okay, and then these are square root of 2 over 2, square root of 2 over 2. Everything can be created from those guys, if you recall. Those are the ones I need you to have pretty much stuck in your head. I say pretty well. I'd like you to memorize them. I'm not going to like force you to. If you're one of those weirdos, it's like, no, I won't memorize it. Well, okay, I can't make you do anything, okay? I can't do it to you. You recall we have the other trig ratios, tangent. Okay, remember that is opposite over adjacent, or better way of thinking it is what? Sine over cosine. Okay. Cotangent, of course, can be thought of as 1 over tan, or adjacent over opposite, or cosine over sine. Okay? So clearly, that one's going to have, both of these guys are going to have issues, right? So for instance, okay, sine over cosine. Well, at 0, the sine is 0 and the cosine is 1, so that's 0. That's hot. But at pi over 2, it's going to be 1 over 0, which is no problema, which is no good, senor. So if you recall, we had asymptotes. Whee! And over here as well, yes? Whee! That's for tangent. Of course, cotangent is similar, obviously, but it goes in opposite directions. I mean, and the asymptotes are at different spots. For instance, for this guy, okay, at 0, it's actually going to have an asymptote. And why is that? Well, because it would be 1 over 0 there. Okay? Secant, Mr. Grimm always had a hard time with this one. This one is hypotenuse over adjacent, but it's 1 over cosine. When I was a kid, I had a hard time with that. Then I just remembered it's backwards, and that's just go with it. Cosecant, it's hypotenuse over opposite. It's 1 over sine. That's it, baby. So it's kind of nice. It's kind of fun to have it out like that. Cool. And so that's that. Again, that should not be that difficult for you. So if you had, again, back here to 30 degrees or pi over 6, and a guy wanted to finish this out, well, we already had cosine. Oops, try to put it on top where it belongs, dummy. Cosine is root 3 over 2. Sine is a half. So tangent would be this guy over that guy. So it'd be, well, I'll do it up here. I really don't need to do it up here. When you invert and multiply, it's 2 over root 3 like that. And you get 1 over the square root of 3. Also known as the square root of 3 over 3. Well, what's cotangent? Well, it's the other way around. Square root of 3 over 2 over a half. So you multiply by 2 over 1. And you get the square root of 3. If you wanted secant, well, that's 1 over cosine. Well, 1 over square root of 3 over 2 is 2 over square root of 3, which that's true. It's also 2 square root of 3 over 3. And then, of course, cosecant 1 over sine is 2. Okay, and you can do that for all of them. Okay, I'm not going to waste a bunch of time doing all of them because you've all seen them before. And that should be just review. Okay, it should be pretty easy review stuff. Love of Pete. I had the Ducks game on in the background just then. I hate the Ducks with a passion. They've already scored twice in about 3 minutes, so that's it. I'm done. All right. Anyway, back to this. There they are. Okay. You can do the same for the rest of them. I'm not going to, go over that again, really, because again, that's something that theoretically you know. If you get stuck on one, for gosh sakes, ask. I'd love to help. The how-to is not hard. The can you help me finish it because I didn't get there. I didn't get the right answer. The love to help. But the how-to is pretty straightforward. It's division, right? Quadrant 1, 2, of course, 3, and 4. If you remember sine, I'm always going to write it cosine, comma sine. They are both positive up here. That means all 6 ratios are positive. Sine, cosine, tangent, cotangent, cosecant, and secant, they're all positive because sine and cosine are both positive. Okay? Over here, it's negative cosine, positive sine, right? So what does that tell me? Well, tangent and cotangent are both going to be negative because sine divided by cosine, if one of them is negative, we've got a problem, right? Well, they're both negatives. Yeah, exactly. Secant will be negative, and cosecant will be positive. By the way, if you ever have an odd number of positives or negatives when you're doing this, you screwed up. Okay, there will always be 2 positives and 2 negatives in all these quadrants. Okay, or 2. There'll always be an even number of each. How about that, right? Down here, they're both negative. So what does that tell me? Well, it tells me that cosecant is obviously negative. Secant is obviously negative. But negative over negative, that means cotangent and tangent are both positive. Over here, it's cosine and sine. And so your tan and cotan are both negative. and then your secant is negative, and your cosecant is positive. Okay. Again, that should be starting to kind of halfway stick in your head. If it's not there all the way, it should be starting to stick pretty good. We will have time to work on this, and I'll spend some time going over some of this with you again in class. I want to get it out there. I want you to go back through it. I want you to find the ones that are kicking your butt, if that makes sense, right? I want you to find the ones. I want you to find the ones where this one's kicking my butt, Groom. Can you help me? These are easy, these are easy, these are easy. Okay, I don't want to waste a bunch of your time when it's like, oh, it's pretty straightforward. Okay. If you recall a radian, okay, and if you've not done this, we may do this in the coming days, but I want you to picture this. Here's a radius of 1. Here's a radius of 4, whatever it is. Doesn't really make any difference. Okay. When this guy rolls all the way 1 revolution to here, okay, how far did he move? He moved 1 circumference. Is that right? 1 circumference. He just rolled down the road. Ditto with this one, except it's going to be, 4 times longer, right? This is also, this is also 1 circumference, right? But it's a bigger circumference, Groom. It is. But listen, I'm going to tell you this right now. How far did he roll? He rolled 2 pi, both of them did, radiuses. Are you with me? They rolled 2 pi radiuses. So in 360 degrees of rotation, okay, that is 1 circumference, which is equal to, of course, 2 pi radiuses. Okay? So back in the day, someone said, listen, you're telling me that 360 degrees is equal to 2 pi, and let's just call them radians. Oh, nice. Why is that important? Is it just to piss you off? No, it actually, in fact, it helps us a lot, because in calculus, in physics, where things are actually moving, there's distance being taken into account, and velocity and things of that nature, we have to take radians into account, because radians is actually tied to a length. 360 degrees is 360 degrees. That doesn't mean diddly piss to me. What's spinning? The radius of the Earth, for God's sakes? Is the Earth spinning? That's different than a little child's fidget spinner, okay? But when we take it into radians and we say it's pi over 2 radians, then pi over 2, that number, which is about 1.57, times the radius is an actual distance. And that's a big deal. Okay, and so I know you guys talked about this a little bit in pre-cal, and probably algebra 2 as far as that goes too. You talked about it a little bit. But when you think about this right here is my angle theta. And what is it? Well, it is 1/4 of the entire circumference, yes? Right, that makes sense? And so it's 2 pi over 4, or it is pi over 2 radians. Okay, that's what theta is here, right? Now, this is the arc length. So S, the arc length is equal to R times theta. This is a big deal. In other words, S divided by R is equal to theta. So if I tell you that we rolled 13.1 feet on some wheel, and this wheel has a 3-foot diameter or 3-foot radius, then we turn this many radians. So 13.1 divided by 3 is about 4.36 radians. Okay, 4.36 radians. And you're like, well, how many degrees is that? I'm confused. Well, if I want to go from radians to degrees, I'm going to take radians times 180 over pi, because that's the conversion. So I'm going to take that times 180, times 180 divided by pi, and I get about 250 degrees. So for this wheel with a 3-foot radius, right, for it to have rolled, let's say this direction, it has to roll 250 degrees. So it's going to roll along, and when it gets over here, whee, and it has rolled 13.1 feet. This guy here is, well, that's 180, so 250 is going to be pointed up this direction, yes? In other words, that's a 250 degrees, or 4.36 radians. That's what that means. And it's really quite straightforward. Okay, now we are only going to really focus a lot on the common ones, pi over 2, pi over 3, etc. But that's not to say that we won't see some other ones, okay? And in fact, we'll do quite a bit of these other ones as well. So you just got to be confident. Now, me, I used to be able to speak Spanish pretty well. I don't anymore at all. It's terrible. But I used to be decent at it. And I was with my friends, and I was working around guys, Mexican guys I used to work with. I was pretty good. Not great, but pretty good. And now, no. And why is that? Well, you don't use it, you lose it. But I never got to the point where I thought in Spanish, ever. Never thought in Spanish. So if you said something to me, I always had to kind of come back to English, transfer it back over and go, oh, okay, and then spit it back out. Ditto in the metric system. So blah, 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 this many meters. I'm like, oh, Judas Priest. I got to convert that back. Okay, yep. Oh, yep. That's a long ways, okay? Because I think in U.S. measurements. I don't think in metric, okay? And I never will. So it's the same way. I'm comfortable with radians, but a lot of times I want to kick back and go, does that make sense, though, in degrees? Yeah, I'd buy that for a nickel. Or maybe not degrees. I might even say it in revolutions, okay? So this is something that's going to happen later on in physics, but I mentioned it here just for fun. RPMs, right? Revolutions per minute, right? So that's obviously 360 degrees times the number of revolutions, right? It'd be how many degrees it spun, right? But if you're doing it in radians, it'd be the revolutions times 2 pi, right? This is a big deal. Because if you're telling me that a wheel is spinning at, I don't know, 5,000 RPMs, my first immediate thought isn't, holy crap, that's fast. My first immediate thought is, well, how big is the wheel? Well, what do you mean? Is it a little matchbox wheel? If it's a little matchbox wheel, I could probably spin it that fast on the end of a drill or something. I could probably get it going that fast. It's a what now? Oh, it's a monster truck wheel. Yeah, I don't think you're going to spin that fast. Oh, wait. Oh, you said it's the Ferris wheel. The 60-foot Ferris wheel? 60 foot in radius? So 120 feet in diameter? Turning 5,000 RPMs? Yeah, I don't think so. Because the guy on the outside is going to be going faster than the speed of sound, dog. That's not going to work very well. Okay? So it matters, right? So degrees-wise, they go the same number of degrees. Radians-wise, they turn the same number of radians. But a point on the outside of the wheel, this guy is going to be going a lot faster than this guy because it matters in terms of the actual distance. And that's where radians will always come into play, okay? Always come into play. So if I tell you that you have a wheel, 15-inch diameter or something, let's just say it's a 1 foot diameter. That 2 foot diameter. Sure, it's a big tire. All right, whatever. And this sucker is spinning at 300 RPM. Sure, I guess. All right, whatever. How fast is that sucker going down the road? I don't know. I know this, though. 300 times 2 pi is how many radians it's going, yes. Times 2 is how many feet per minute it's going. So that's 600, 1,200 pi. 100 pi. Is that number about that many feet per minute, right? So if I divide that by 5,280, I get about 0.71 miles per minute times 60. This thing is going about 42 miles an hour, 43 miles an hour. Okay, that's going to be helpful. If you did it in terms of degrees, it would be an extra step added in there because, yeah, we wouldn't want to do it that way. Radians is where it's at. Radians is the best, okay? Something else I mentioned in the last section, we said that sine is an odd function. And so, once again, the sine of negative theta is equal to the sine of positive theta. I do want you to think about this in two different ways. First of all, in the unit circle, here's theta. Here's negative theta, right? You see that? They clearly have the same cosine, don't they? Remember, cosine is even, right? So in this case, the cosine of negative theta, that's disturbing. The cosine of negative theta is equal to the cosine of positive theta. Well, here, check it out. They both went the same way to the right, yes? But look at their signs. This one's positive, this one's negative. That's one way I want you to visualize it, right, in a unit circle. I also want you to be able to visualize it on this graph. Here's cosine. Here is negative theta. Here is positive theta. Check them out. They're the same height. Here is sine. Bloop, 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 bloop. Here is negative theta. Here is positive theta. Check it out. They are the same height, but what? Opposites of each other. I want that clear in your head. Again, that comes from the concept of odd and even functions. Okay? All right. Oh, shoot. About dropped that on my tootsies. That would have hurt. All right. A couple of identities. You guys told me this one the other day. I want to spend just a minute talking about a couple more of them that kind of come off of this guy. That is the Pythagorean identity. Now, remember, the cardinal rule of algebra says that whatever thou doest to one side, thou must also doest to the other side. So if I divide everybody by cosine squared, because I can, obviously, what do I end up with? Well, I end up with 1 plus, hey, that's tangent squared, is equal to, hey, that's secant squared. That's exactly right. That is one of the identities. But guess what? This guy is also one of the, it's also called the Pythagorean identities. There's 3 of them. And why is that? Well, because they come from the same guy. If this is divided by sine squared, you end up with cotangent squared plus 1 is equal to cosecant squared of theta. Oops, there you go. A lot of times you'll see this one written as secant squared theta minus 1 is tangent squared. This one probably gets used more than the other one. So you'll see the regular old Pythagorean identity, that guy. You see this one, and this one show up quite a bit. Okay? Be familiar with them. Like, you asked me to pull that one out of my hat. I can't. I always go back to this one, and then I go, oh, do you want cotangent? Well, I better divide by sine squared. You with me? And that's how I conjure it up. Now, I've done it long enough. I've pretty well got it memorized, but over summer, do I forget sometimes? Sure. And then it's simply a matter of knowing where it comes from. Where did that come from exactly? What's that about? Okay? These double angle formulas and half angle formula stuff, I want to run these through you real quick. If you take the cosine of pi over 2 minus x, what does that equal to? Well, before you answer, remember these are in right triangles, for heaven's sakes. All right, I want this one to be x. How exciting. What's this guy here? Well, this guy is 90 minus x, right? Or in other words, pi over 2 minus x, right? Because these two angles, this one and this one, have to add up to 90, right? So the cosine of this angle, would be the adjacent over the hypotenuse. Well, what is that in relationship to x? Well, that's opposite over hypotenuse, so it's equal to the sine of x. And the sine of this angle is exactly what you think it is. It is equal to the cosine of x because, again, sine is going to be opposite over hypotenuse. Well, that's this opposite for this fella is adjacent to this guy. Okay. Yeah, we'll do this angle addition formula. I want you to be comfortable with these guys. I want you to be comfortable with them. I don't need you to memorize them. I want you to be comfortable with them. Sine is a same sandwich. It's a sine-wich is actually, I believe, what Levi coined it back in the day when he was in high school. Oops, I did it backwards. I did it backwards, stupid. Come come on, Jay. No, you did it right the first time, dumbass. You got it written down, then you screwed it up. Cosine x, sine y. That's right. Yay, it's a sandwich. Because the sine's on the outside and you're making a sandwich out of it. You with me? That's plus or minus. Plus or minus. And cosine is similar, except it's cosine x, cosine y, minus plus sine x, sine y. I want you to be comfortable with them. I want you, when you look at them, think, oh, I've seen this before. Yeah. I don't need you to know them really well. I just need you to have seen them at some point. All right. So the ones that come to my mind is, well, what if I take 2x? What's the sine of 2x? I don't know. But I do know that's the same thing as the sine of x plus x, which would be the sine of x, cosine of x, plus cosine x, sine x. But Groom, those are the same. I'm well aware. So 2 sine x, cosine x. This guy right here is what I need you to know. I need you to know that. But it came from this angle addition formula. But I need you to know that because later on, this is a son of a gun to work with sometimes. This isn't nearly as bad. Sometimes this is gross. This is easier to work with. Everything we teach you, if we're not using right away, pretty much is going to come back to bite us or, be helpful to us when in calculus. And this is what I'm talking about right now. What about cosine of 2x? Well, that would be cosine x, cosine x, minus sine x, sine x. Wait, that's cosine squared minus sine squared. It is. This is equal to that. Yay! And I can make that substitution. Now, that guy right there is useless to me most of the time. But let me tell you what, friends. Sine squared plus cosine squared is equal to what? 1. But let me ask you this question. What's cosine squared equal to? What's 1 minus sine squared? Well, that means I could substitute. I'm going to get 1 minus sine squared minus sine squared. That's 1 minus 2 sine squared. And that is another way of saying this guy right here. Likewise, sine squared is equal to 1 minus cosine squared. And so if you put that one in, you're going to get cosine squared minus 1 minus cosine squared. And when you do that, you're going to end up with 2 cosine squared x minus 1. This guy and this guy being equal to this guy are the most important, not this, not that, okay? We use that to get to the other two, okay? These two are very useful to us in calculus, very useful. Now, something that you'll run into later on in calculus, and I'm just going to show it to you now, because this is why we're running over this. Are you with me? There is a reason to do this. This is not to, again, to piss you off. A lot of times we want to know what x is, but we only know 2x. And you're like, what's divided by 2? Okay, well, I don't know what it is. I just know what the cosine of 2x is. Oh, no, exactly. So watch. You're telling me, Groom, I could just do this plus 1 divided by 2? That's right. Is equal to the cosine squared of x? That's right. Well, I just have to square root. Yeah. Cosine of 2x plus 1 over 2 is equal to cosine of x. If you told me this, I would kind of like go, well, almost. Remember, it's a plus or minus. Now, think about that for a minute. If this is 2x right here, if this were 2x, then obviously 1x is down here, and obviously it has the same sign. Does that make sense? Because it's in the same quadrant, right? But what if your 2x was over here? What if this was 2x, like it was 120 degrees? Half of that puts me back over here in the first quadrant, which means I'm going to have a positive cosine. Now, that'll chase itself out in the wash later on, but this plus and minus is very important. Very important. So you've got to handle that. Keep track of that. The same thing could be done up here using this guy. I'm not going to do it. We'll leave that for later in the text. But it's introduced in this section, so I kind of wanted to throw it at you just for a good time. Okay? And Yeah, I believe that's all I wanted to talk about for section 4. That gives you something to chew on. That gives you quite a bit to chew on, actually, before next time. And then you can have time to answer questions and stuff. All right.